So hi guys, today I'm going to tackle the chapter 5 entitled Ethernet Summary. So I'm going to tackle the summary of the chapter 5 Ethernet. So the OSI physical layer, it provides the means to transport the bits made up a data link layer frame across the network media. So Ethernet is now the predominant LAN technology in the world. Ethernet operates in the data link layer and physical layer. The Ethernet protocol standard define um, many aspect of network communication, including the frame format, frame size, timing, and encoding. So, so now let's proceed. So, for the first one, Ethernet. So for the Ethernet, the Ethernet again. So the Ethernet, it is the most widely used LAN technology today. So Ethernet operation in the data link layer and the physical layer. Um, so it is a family of a networking technologies that are defined in the triple E 802.2 and 802.3 standards. So yeah, so the Ethernet, it is the most widely used LAN technology today. So for the next one, so we have here. So before that, Ethernet, it support the bandwidth of 10 MB, 10 MBs, 100 MB, 1000 MB, and or 1 GB, 10,000 MB or 10 GB, 40,000 MB or 40 GB, 100,000 MB or 100 GB. So So the Ethernet MAC sublayer, it has two primary responsibilities, which is the data encapsulation and the um, media access control, or the MAC. So for the data encapsulation, the data encapsulation process includes a frame assembly before transmission and frame assembly upon reception of a frame. Informing the frame, the MAC layer adds a header and trailer to the network layer PDU. So the data the data encapsulation, it provides the three primary function, which is the frame delimiting, addressing, and error detection. So now let's go to media access control, which is the MAC. So the second responsibility of the MAC sublayer is the media access control. So the media access control, it is responsible for the placement of the frame on the media and the removal of frame from the media. So the Ethernet 2 frame fields, we have preamble, destination MAC address, source MAC address, the Ethernet type, data, and FCS. So the preamble, it has 7 bits, and the destination MAC, it has uh, 6 byte, preamble 7 byte, destination MAC address 6 byte field, source MAC address, it has also 6 byte field, the Ethernet type, it has 2 byte field, the data, it has 46 to 1000 bytes. For the FCS, it has 4 byte. So again, it is a Ethernet 2 frame fields. So the MAC address, the MAC address structure, the MAC address value, it is direct result of IEEE unique enforce rules for vendors to ensure globally unique address for each Ethernet service device. So the rules established by IEEE require any vendor that sells Ethernet device to register to IEEE. So the IEEE it requires a vendor to follow the two simple rules. So it is the all MAC address assigned to a NEC of other Ethernet devices must use the vendor's assigned OUI as their first 3 bytes, and all MAC addresses with the same OUI must be assigned a unique value in the last 3 bytes. The next one is the unicast MAC address. So the unicast MAC address, in the unicast MAC address is the unique address, and when a frame is sent from a single transmitting device to a single destination device. So for the next one, we had the broadcast MAC address. So for the broadcast MAC address, the broadcast packet contains a destination IPv4 address that has all ones in the host portion. So this numbering in the address means that all hosts on the local network will receive and process the packet. So many network protocols such as DHCP and ARP use broadcast. For the next one, we have multicast. So for the multicast MAC address, the multicast MAC address it's a multicast address allows a source device to send a packet to a group of devices. So destination that belongs to a multicast device are assigned to a multicast group IP address. So the range of IPv4 multicast address. So yeah. So for the next one, you have the learning MAC addresses. So we learn learn examine the source MAC address and the forward examining the destination MAC address. So every frame that enters a switch is checked for new information to learn. So it does this by examining the frame source MAC address and port number where the frame entered in the switch. So if the MAC address does not exist, it is added to the table along with incoming port number. So for the forward examining the destination MAC address, if the destination MAC address is a unicast address, the switch will look for the match between the destination MAC address of the frame and an entry in its MAC address table. So if the destination MAC address is in the table, it will look forward the frame out of the specific port. For the next one, switching packet forwarding method. So switching packet forwarding method. The first one is the a stored and forward switching and the cut through switching. So a store a store and forwarding switch receive the entire frame and computes the CRC. So if the CRC valid, the switch locks up to the destination address. So which determines the outgoing interface. The frame is in then forward the correct port. So in cut through, um, switch forward the frame before it's entirely received. So it is a minimum the destination address of the end of the frame must be read before the frame can be forwarded. So on the difference between the store forward and the cut through. The store forward, it switch the entire frame and completes the CRC, even if the CRC is valid. And then for the cut through, it forward the frame before it entirely received. So for the next one, we have two methods of memory buffering. So it is the port-based and the shared memory. So yeah, the port-based memory buffering, in port-based memory buffering, frame are stored in queues that are linked to specific incoming and outgoing port. So a frame is transmitted to the outgoing port only when all the frames ahead of it in the queue have successfully transmitted. So for the shared memory buffering, shared memory buffering deposit all the frame on into a common memory buffer that all ports on the switch share. So the amount of buffer memory requires by port is dynamically allocated. So the frame in the buffer are linked dynamically to the destination port. For the next one, also the two types of duplex settings used for communications on the Ethernet network. So we have the half duplex and the full duplex. So the full duplex, both ends of the connections can send and receive simultaneously, and for the half duplex, only one end of the connection can send at a time. So on full duplex, both end connection can send and receive, and the half duplex, only one end of the connection can send at a time. So there are two primary addresses assigned to a device on an Ethernet LAN. Just the physical addresses, the MAC addresses, and the logical addresses, the IP addresses. So, so the physical addresses, it used for Ethernet NIC to Ethernet NIC or Ethernet NIC to an Ethernet NIC communication on the same network. So for the logical addresses, the IP address used so for the IP address, it's used to send the packet from the original source to the final destination. For the next one, so when a device sends an Ethernet frame, it contains these two addresses. We have the destination MAC address and the source MAC address. So in the destination MAC address, the MAC address on the Ethernet NIC, which will be either the MAC address of the final destination or the router. So the MAC address of the Ethernet NIC, so it will be so like what I said, either the MAC address of the final destination or the router. So for the source address, the MAC address of the sender's Ethernet and NIC. So we have in the ARP broadcast, as a broadcast frame, an ARP request is received and processed by every device on the local network. So on typical business network, this broadcast would probably have minimal impact on the network performance. However, if large number of devices were to be powered up and all start accessing network service at the same time, there could be some reduction in the performance for a short period of time. So the next one is for the ARP spoofing. So some cases in the use of ARP can lead to a potential security risk, so known as ARP spoofing, so or ARP poisoning. So there is a technique used by an attacker to reply to an ARP request for an IPv4 for addressing belonging to another device, such as the default gateway. So the attacker send the ARP reply with its own MAC address. So the receiver of the ARP reply will add the wrong MAC address to the ARP table and send to this packet to the attacker. So that's how it done by the attacker. So again, so that's all for the summary of the chapter 5 titled Ethernet. So I hope you guys learn in this chapter and from what I see. So thank you guys again for watching.